Hello everyone. Today I will talk about dynamic enumeration of similarity joins. This is a joint work with Pankaj Agarwal, Xiao and Jun Yang. Let's start with the introduction. Assume that we have two sets of points A and B in D dimensions. In this project, we study the similarity join problem, where we aim to report all closed pairs A, B. Given a distance function phi and a distance threshold r, 2 points A, B are close if their distance with respect to function phi is at most r. The goal of our project is to construct a data structure so that we can report the closed pairs efficiently. More specifically, we aim to enumerate them with delay guarantee. With delay guarantee, we mean that the time between the enumeration of two consecutive pairs should be bounded. Here it is important to highlight the difference with other reporting queries, where the goal is to report all results in time that depends on a sublinear function with respect to the number of items n, plus the output size. Here we define the delta delay enumeration, saying that the maximum amount of time that the user can wait until we show a new result is delta. In such problems of finding similar items, we would like the user to be able to insert or delete objects from the sets. Hence, our data structure should support insertion or deletion of a point efficiently. In many cases, it is too expensive to find all similarity join results. Hence, we define the epsilon approximate similarity join problem, where we must return all pairs within distance r. We should not return any pair with distance more than 1 plus epsilon times r, and some pairs with distance between r and 1 plus epsilon times r might be reported. There is a lot of related work on similarity join queries and other related problems, so here I only show some representative papers. For instance, in databases, there are efficient data structures for the dynamic enumeration of conjunctive hierarchical queries with linear space and constant update and delay guarantees. Conjunctive queries focus on equal join queries, which is a special case of our problem where the threshold r is 0. We extend this line of work with similarity join queries between two tables. In theory, there is a lot of work on range searching. Given a set of points in D dimensions, the goal is to build a data structure to answer reporting or aggregation queries among points in a query rectangle or half space or generally any QSA. These data structures are useful for our problem, but they cannot answer directly the problem of dynamic enumeration of similarity joins. Finally, there are papers on the reporting neighbors problem. In this case, we have a set of points and the goal is to find and report all pairs within distance r. There are many differences with our problem definition. For example, we have two sets of points and we want to report only the close pairs between points from different sets. Furthermore, the reporting neighbors problem is an offline problem. However, in our case, we care about the online version, constructing a dynamic data structure to support insertions and deletions and report the close pairs efficiently with delay guarantees. Before we start showing our results, we specify some of the parameters and functions we use in this work. The dimension D can either be constant or very large, so we propose results for both cases. Furthermore, in this project, we mostly focus on LP norms as distance functions. Then notice that the distance threshold R can either be fixed, meaning that it is known in the pre-processing phase while we construct the data structure, or it can be part of the query. In the second case, we need to construct the data structure so that we can answer a similarity join query for any possible threshold R. Finally, we provide results for both the exact enumeration and epsilon approximate enumeration problem. Here are our first results when the dimension D is constant. For exact enumeration and when the distance threshold R is known in the pre-processing phase, our results depend on the metric we consider. For the L1 and L infinity, we have a near linear space data structure where both update and delay complexities are near constant. Without tilde notation, we hide log to the d factors of n. Furthermore, the update time is amortized. For the L2 metric, we have a near linear space data structure with update and delay time order n to 1 minus 1 over d plus 1. We can see that for the L2 metric, the complexities of update and delay are worse comparing to the complexities we had for L1 and L infinity metrics. We can actually show a lower bound for the L2 metric, saying that we cannot hope for a near linear space data structure with near constant update and delay guarantee. Then we provide results for the epsilon approximate enumeration problem. Here the results hold for any LP norm. If R is known in the pre-processing phase, we can have a linear space data structure where both update and delay are roughly order epsilon to the minus d. If R is part of the query, then our data structure uses more space, which is order epsilon to minus d times n. The update time is roughly order epsilon to minus d, and it has constant delay. We also provide results for high dimensions. Here we consider the epsilon approximate enumeration problem, and our results hold for the L1, L2, and the Hamming distance. These results hold for a fixed parameter R, but we can extend our data structure to work even if R is part of the query. We built a data structure upon the well-known locality-sensitive hashing. We get a data structure with space order dn plus n to 1 plus rho with update and delay guarantees roughly dn to the 2 rho. Here the O tilde notation hides a log to the 2n or log to the 3n factor. The parameter rho is defined as the quality of the LSH family. For example, for the L2 metric, rho is bounded by almost 1 over 1 plus epsilon squared. Before we go through the details of our data structure, we give the high-level framework of our solution. One way is to model similarity join as a bipartite graph G with a set of nodes A and B. Two nodes A, B are connected if their corresponding points are close. Our goal is to build a data structure so that we can update this graph G efficiently. Unfortunately, if we do it in a naive way, we would need quadratic space and linear update time because a point in set A can be close to all points in set B. Instead, we use a compact representation of the graph G with a set of disjoint biclics. In particular, we define a tripartite graph G prime, where in addition to the set of nodes A and B, it has a new set of nodes C that represents the biclics. Furthermore, E1 is the set of edges from nodes in A to the biclics, and E2 is the set of edges from the nodes B to the biclics. In the example here, the biclic C1 contains the point A1 from set A, and the points B1 and B2 from set B, meaning that A1 is close to both points B1 and B2. Hence, we store and maintain a set of nodes C representing the biclics as the user insert or remove points. However, even in this case, we cannot afford to maintain the sets of edges E1 and T2 explicitly. Instead, we use geometric data structures to recover the edges incident to a biclic with delay guarantees. In this presentation, we will first show the results we have for the exact enumeration of the L infinity metric when the dimension D is constant. Then I will present the main ideas for the epsilon approximate enumeration in high dimensions. Let's start with the exact similarity join under the L infinity metric. For simplicity, we consider that the dimension D is 1. This is without loss of generality, and all our results can be extended to any constant dimension D. In addition, since the distance threshold R is fixed in the pre-processing phase, we can also consider that R is equal to 1. As you can see in this figure, a point A has distance at most 1 from a point B, if and only if A lies in an interval of length 2 and center B. So let's call this interval B bar, and let the set B bar be the set of all intervals of length 2 that have as a center a point from set B. In higher dimensions, we can consider that B bar is a square instead of an interval. The main data structure we will use is a range tree, which is used for reporting or aggregation range queries in general over a set of points. A range tree can be defined in any dimension D, but here we only describe it for D equals 1. In this case, the range tree is a balanced binary search tree of height order log n. Each point is stored in a leaf node, and an inner node is called the canonical node of the tree. Each canonical node V is associated with an interval IV containing all points in the leaves of the subtree with root the node V. For example, as you can see in the figure, node U has the interval IU, including all points in the leaves. Finally, it is known how to make the range tree dynamic, supporting efficient point insertion and deletion. If we have a query interval I, then using the range tree, we can find the set of order log n canonical nodes that include all input points that belong in I. For example, in this figure, if the interval I contains these points, then the query procedure will find these two red nodes as the canonical nodes of interval I. Notice that these red nodes contain all input points inside the interval I. For our data structure, we construct a dynamic range tree TA for the set of points A, and the dynamic range tree TB for set B. Furthermore, for each node V of the tree TA, we store a counter JV with a number of intervals B bar that have V as a canonical node. Our main goal is to store and maintain a set of active canonical nodes C of the tree TA. We say that a node V of the tree TA is active if the following two conditions hold. First, the interval IV contains at least one point of A, and second, the node V is the canonical node of at least one interval B bar, or with other words, JV must be at least one. The space of our data structure is the space of storing two range trees, which is near linear on the input size. Then we briefly talk about how to update our data structure. If we insert or delete a point B from the set B, we update the dynamic range tree TB, and then we find the canonical nodes of the corresponding interval B bar in the tree TA. Let S be this set of canonical nodes in TA. For each canonical node U in S, we update the counter JU by increasing or decreasing it by 1, and depending on the value of the counter, we might insert or delete it from the set of active nodes. The update time is near constant because this is the time that we can find the canonical nodes of a query interval in a range. For example, in 1D, it is order log n. Next, assume that we insert or delete a point A. We first update the dynamic range tree TA. Then, for each new inserted or modified node U of TA, we need to compute the counter JU so that we can decide if U is an active node or not. From the definition of the range tree, an interval B bar has node U as a canonical node, if and only if the interval IU is fully contained in the interval B bar, and the interval I of the parent of U is not fully contained in the interval B bar. In the paper, we saw how to rewrite these conditions as two linear constraints with respect to the coordinates of points in B. Hence, we can use the pre-computed dynamic tree TB to get the counter JU, which is the number of intervals in B bar that have U as a canonical node. The query time is constant, skipping the log n factors, since this is the time to run a counting query in the range tree TB. Finally, for the enumeration procedure, for each active node V, we get all points of A in the subtree of TA rooted at V, and then using the range tree TB, we can get all points in B whose corresponding intervals B bar have V as a canonical node. Hence, the delay guarantee is near constant, which is the query time on tree TB. Before we continue with our next results, we saw how our data structure is mapped on the high-level framework I described earlier. Notice that the active nodes of the tree TA represent the biclics. In order to get the set of edges E1, we only use the tree TA. These are the points that are included in the leaf nodes of a subtree of TA rooted at an active node V. In order to get the set of edges E2 efficiently, we use the tree TB to get all intervals B bar that have the active node V as a canonical node. Next, we saw some extensions of our solution from the L infinity metric. We can extend our method to work for the L1 metric. In particular, we can map the similarity join problem under the L1 metric to constant instances of the similarity join problem under the L infinity metric. For the L2 metric, the main idea is to use a partition tree instead of a range tree. As I mentioned earlier, we can show a lower bound for the L2 metric, saying that for d greater than 3, we cannot hope to get a near linear space data structure with constant update and delay. We prove it by a reduction from the units fair reporting problem, where given a set of points in b dimensions, the goal is to construct a data structure so that given a query unit sphere, we report all points in the sphere efficiently. Next, in the rest of the time, we give an overview of our data structure in high dimensions. Our data structure is built upon the well-known localities sensitive hashing. So here is a very brief overview of LSH. It is mainly used for approximate nearest neighbor queries in high dimensions. The main idea is to generate a set of random hash functions from a sensitive, as it is called, family of hash functions. Each hash function defines a set of buckets based on the different values that the hash function can take. Every point is stored in one bucket for each hash function based on its value. The space of the LSH data structure is roughly ordered dn plus n to 1 plus rho. Given a query point, we visit the buckets that the query point lies in and search if there is a close point among the first order dn to the rho points we check. If we find a point with distance less than 1 plus epsilon times r from the query point, we return it. Otherwise, we say that there is no point within distance r. For our problem, we build an LSH data structure over the union of the sets A and B. The main idea is to maintain a set of active buckets, which are the buckets that contain at least one close pair to report. So for each bucket, we store a representative close pair in case that we found one. We explain later how we check if there is one close pair. For example, assume that we have this bucket here that contains a subset of the points in A and a subset of the points in B. And let's say that we found that the pair A1B3 has distance at most 2 times 1 plus epsilon times r. In this case, we store the pair A1B3 as the representative pair of the bucket. There are a few different cases on updating the data structure depending on the insertion or deletion of a point in A or B, but here I show the most interesting case. Assume that we need to remove the point B4 from the set B. We need to go through all buckets that contain B4 and remove it. For example, in this bucket that we had before, we go and we remove B4. Notice that the representative pair remains the same, so this bucket is still active, hence we do not need to do anything more. However, assume that we want to remove the point B3. Again, we go through all buckets that contain B3. In our bucket here, we can see that B3 is a point of the representative pair. So after the deletion of B3, we are not sure if this bucket is still active or not. In order to decide if the bucket is active, we take m points from the subset of points in A in the bucket and m points from the subset of points in B in the bucket, and we measure their pairwise distances. We explain later how we define the parameter m. If we find no pair with distance at most 2 times 1 plus epsilon times r among the m points from A and m points from B, then this bucket is not active anymore. Otherwise, we find a new representative pair with distance at most 2 times 1 plus epsilon times r, and this bucket is still active. The correctness of this procedure follows from the next observation. For any pair AB with distance at most r with high probability, there is at least one bucket C, such that first, both points A and B lies in bucket C, and second, there are no m points A prime in C and m points B prime in C, such that all their pairwise distances are greater than 2 times 1 plus epsilon times r. We can show this result if m is roughly order n to the row. So in other words, here we show that for any closed pair AB, there will be at least one active bucket that contains both A and B with high probability. For the enumeration, we need to go through all active buckets and report the closed pairs we find. After reporting the representative pair of an active bucket, we update the representative pair if there exists one, and we continue until all buckets are not active. One problem that we might face is that a pair of closed points A and B might belong to multiple buckets. However, our enumeration procedure must return a pair only once. Hence, we have a deduplication procedure so that when we find the pair AB with distance at most 2 times 1 plus epsilon times r, we make sure that we will not report the same pair again. We do it by following a specific order of the enumeration and by temporarily marking the points we have already reported. More specifically, when we report a representative pair AB, we mark point B with a marker XA. Then we lock point A and we search over all buckets that contain A to find closed pairs AB prime for points B prime that are not marked by XA. After we report all closed pairs AB prime, we mark A with X and we continue with the next representative pair, making sure that we will not include points from set A that are marked by X in the representative pairs. Skipping the details, we conclude with a data structure of space order dn plus n to 1 plus row, while the update and the delay guarantees are order dn to the 2 row. Our data structure returns all pairs within distance r with high probability. It does not return any pair with distance more than 2 times 1 plus epsilon times r, and it might return some pairs within distance r and 2 times 1 plus epsilon times r. There are still some interesting open problems. In this project, we focus on pairwise similarity join queries, but there are more complicated queries we can consider, like cycles. It is also interesting to study our problems under more general metrics or semi-metrics. Finally, in this project, we focused on worst-case guarantees. However, in many real-world datasets, the datasets and the update sequences are not arbitrarily bad. So it makes sense to study our problem under some more realistic cases. And with that, I conclude my talk. Thank you.